morning, everybody. Thank you for being here, and I would like to start, and before I forget, I would like to thank the organizers, the NSF, and the Bulgarian Academy of Sciences for having me here today. And what I will be talking about is about what it says there, precisely. So I'm going to try and show you some theoretical considerations that lead to a mathematical model, that lead to something which can be implemented in the laboratory. And I will just show you how we do that. I'll try to at this point, I'm trying to get familiarized with the system. So I will try to describe everything I have in about 20 to 25 minutes to leave time for questions. What is the motivation for wanting to make some form of life, whatever it is, artificial, whatever it is, not based in biochemistry? Why would you like to do that? Well, because you want to see if you can actually generate a system ex novo, or equivalently, in less sophisticated Latin, de novo, from scratch, and see if you can actually generate a system from scratch totally, where the system boots up the same way your computer boots up under the full control of chemistry, and operating in a particular environment. In other words, the system that I will be shown to you, which is totally experimental, but you will see the results of the experiments, is a system which is actually able to do what it says here. It boots up in a particular environment, but you could change the environment and you could change the chemistry, and eventually will also do that. So this is trying to see if you can construct life in some way. For example, if you want to emulate the function of flight, you don't go ahead and build a bird with feathers and everything else. If that's what you want to do, then your name is Icarus, and then you're going to go to southern Italy with wings, artificial wings, and then you're going to use wax. It's going to be July, and then you go to the top of a temple, then you try to fly. No matter how much you flap, the wings break, you crash, and you say nothing. So, but if you understand the principles of flight, like you understand Bernoulli's theorem, and you understand that if you move air in a particular direction at a particular speed, then you will generate lift. You can generate lift. Then you are one of the right brothers, and then you can invent a plane. So a plane doesn't look like a bird, yet it has the same function, the function of flight. So what I'm going to be showing to you is something which attempts to do an instance of this type of philosophy. So, can it be used for the origin of life, origin and evolution of life on Earth? Well, if it does, then it will be way before RNA, way before life as we see it here, and so on and so forth. But it could contribute to understanding proto-cells, that is to say, cells which are before any cell we know today. Not a prototype of cell. I'm not building prototypes of cells. So if you want to call proto-cells what we do, it means before cells. And it's not a prototype of current cells. And then what I'm going to be discussing was motivated originally in trying to understand if there are any other possibilities for life in the universe. The universe is huge. There's many possibilities for chemistry. So what is it? Is there chemistry which is now the one that is making me alive today, or that is making us alive? Then is there any possibility that you could emulate all the functions of life without appealing to biochemistry? And if this is the case, then this would be, if what we will be showing to you now works, then it would be a case of what Bernard, an English biophysicist, Bernard, called generalized life. Not many people know about this, but if you look at his book about the origin of life, you can find out already a vision of this in the 1960s, which is what he published his work. So what are going to be the questions for today? So the questions for today will attempt and the path, the conceptual pathway that we will follow. So it is, we will try to use the scientific method, which today involves quite a few important components. One is mathematical representation. Of course, I am corrupt. I'm a physicist. So the first thing you begin to think is there a mathematical representation of the phenomenon? Which the answer to that will be yes. And then can you do in the current mathematical scientific method, you need to do, you can also do computation to aid in the description, in the scientific description of the phenomenon. You will see that from this mathematical representation you can actually solve it in a computer. And then what can you learn from here so that you can do experiments? In this case, it's not observation, so that you can do experiments. So the first question that you ask, and will be answered positively, is can a generic mathematical physics and chemistry at high level, meaning little level of detail, description of the properties of life be given? And then could one use this description to actually generate some form of experimental corroboration? That requires that you have a very clear idea of what you mean by life. And here is what we mean by life. This has been discussed in many places. I, for example, in the 50th anniversary book published in Chemistry University Press about 50 years of Schrödinger's Quality Life book, lists all of this for properties. Many other people have been discussing this, including myself about 20 years ago. And then there is a beautiful book by Paul Nurse, which irritates me in the title, but it's a wonderful book. The book irritates me because it's also called What is Life? And to me that is a sacred title for a book. But anyway, so living systems, all living systems are characterized because they're capable of using chemistry. This is very important. Using chemistry, they're capable of handling information, which means communication, it means computation, chemical computation, communication of chemical information. Then metabolism, that is to say the system is capable of using simpler parts in its environment, is capable of making its own parts and then parts that will be used for its self-reproduction. The system is capable of doing self-reproduction, that is to say the system as a system generates the seeds and the production of new systems, daughters, whatever you want to call them, and then the system needs to evolve. We could spend a year discussing all of this properties in detail. Of course, here we don't have the time. But what the question that you ask, and you always ask in physics, is can we integrate or unify these functional properties, these four functional properties? And the answer is it will turn out to be possible. But before I do that, let me show to you how biology, extant biology, actually unifies those properties. This is a very abstract representation of the cell division cycle. It's a property of all living systems. This figure here is taken from Murray and Hunt, a book dedicated to that. It's a beautiful book. And the figure is an abstraction of what happens throughout life. Here, in the left axis, you have the cell mass. In the right axis, you have the amount of DNA in the nucleus. Notice that the units here are 1, 2. The units here is a little bigger. So what happens is that the system begins to work. A living system begins to metabolize and make mass. It increases its mass. It will reach a point where the mass is 2, and at that point, the system will actually replicate. They say it's a different path is followed by the DNA. The DNA stays constant, and then it comes to a point where the DNA reaches value 2, and at that point it doesn't need more. It follows a series of processes, and there is chromosome segregation, and a little bit after, which occurs a little bit before. You have twice the mass, and then the system, when it reaches the mass, replicates. So this is the generation of another system. And so biology actually unifies all those properties in this system by displaying the cell division cycle. And so, is there any such thing, or is there a way in which we could somehow understand what we will need to do in order to see if we can reproduce this? Well, let's look for inspiration. And the inspiration is provided of unification of the properties. We're going to show how to unify these 4 properties and see if we can produce equations that actually generate this. For this, the model behind our head is Maxwell's equations. Maxwell knew about the Coulomb's law and the Biot-Savart law for magnetism. Then, imagine that this is information, and this is, for example, metabolism. So Maxwell knew how to put these 2 together in mathematics. He came up with Maxwell's equations, and then there were predictions of the theory. The predictions, he just wrote the equations mathematically, because he knew math, he knew how to put these forces together. And then a few years later, 15 years later, or 25 years later, Hertz discovered the presence of a prediction here, which is that there were electromagnetic waves. And then our friend Marconi and others developed the radio and so on and so forth. So can you do something similar for biology? Well, you would want to write the minimal system, and a minimal system would be, I don't want to call it the spherical cow, but the minimal system would require something which incorporates the notions of chemistry, like mechanism to transport a mechanism to transport the molecules, diffusion, for example, and another mechanism to react molecules. So this can be also, this tells you that the class of equations are diffusion reaction equations for the molecules. Substances, then at least you can do the most minimal system you can come up with is one for the cell itself to be represented without any level of detail, which we will call V, and one for the fluid without any level of detail, U. But you need to put together another component, which is the waste used for, by the living system. And then the environment is quite important, and then you can choose a random intrinsic component, which will have to do with things that happen inside or things that happen in the external environment. And you can actually unify if you go and look at the properties, the polynomial properties that need to be satisfied by the reaction terms. You can put them together, and to make a long story short, a very long story short, you can come up with the model of the cell, where the cell has a lattice, and at each point in the lattice, you can constrain the previous terms in such a way. You constrain it with mass action kinetics, and you can actually find out that all those properties, or all those properties in a unified way, are satisfied by these stochastic parabolic nonlinear differential equations, Spanos, like somebody used to call them. So if you want details for this, you can look at this paper by Alberto Perez-Mercader and myself, no family relation, even though we have the first family name. It's in Physics of Life Reviews, and it appeared this year. And then there is a paper in Physical Letters in 2003, another one in 2004, which describes a lot of the phase space of this model, etc. So when you put that model in a computer, and this is not a great simulation that I have here, but it's the one that I was able to download today. When you put that in the computer, you give a particular type of boundary conditions. Here is what happens with those equations. You can see that it looks like a cocktail of cells. And in fact, if you look at one of those domains, you find out, if I can find my pointer, you find out that the domain grows, and you can here, represented here is the information, the entropy, and here you have the size. So the system, I'll do it again, the system actually executes a form of the division cycle. This was quite interesting and quite surprising. And then we said, can we use this to actually come up with a realistic representation? Well, you can use a material representation. So you could take the take of my compatriot Pablo Picasso, say everything you can imagine is real. Well, depends on how much wine you have drunk or how many joints you have smoked. But if you have the scientific method, then things are different. You have a guidance. Okay. So what do you learn? You learn that there are a number of problems that you need to solve. If you want to put up a system, which is you want it to do autonomously, it has to go from a high entropy sort of system, which is homogeneous, for example. It has to go from a high entropy to lower entropy and so on. You need to combat a problem, a real problem, which is the arithmetic bingo, which Dimitar alluded to the other day. He cited this book by Felix Serratosa, who was 2 offices away from my office in Spain, in Madrid, when I was a junior, like a tenure assistant professor in Spain's National Research Council. Well, you can actually do this, and the way you do that is because the equations tell you something very important. What the equations tell you is that those solutions I showed to you earlier are implemented only if you have a particular type of boundary conditions, which you can implement in chemistry. And what you do is you want to make a container. The container has to be uniform as possible, and there's ways of doing that. There's advances in chemistry which have happened in the last 15 years or so. There's a way of polymerizing, which is called polymerization, used in self-assembly, where you start with very simple molecules. This is polyethylene glycol, it likes water, and then you can have photochemistry that actually will attach here monomers. You can choose a monomer, like for example, something called HPMA or acrylonitrile, in such a way that when the monomers join here, it will generate a molecule which has a hydrophilic part and a hydrophobic part. The 2 of them will self-assemble, and then what will happen is, and you will see how that happens, there is a certain critical value that happens, that is reached, critical value of the concentration, and then this system will self-assemble into my cells. So this is the original soluble material that you are adding here, the hydrophobic polymer or tail of the system. Then the system will self-assemble, and first will generate spheres or micelles. Then this goes through a series of dynamic reference transitions, which are controlled by the chemistry which is happening here. This is very important, that is all under the control of chemistry. I am relatively proud to say, I'm not a very proud person, but I'm relatively proud to say that when we sent this for publication in Specialist Journal to validate, they actually gave it a cover. So that was quite nice. And how does the apparatus look like? This is what it looks like. There's a reactor here, a simple reactor there. I'm not going to spend too much time on that, except flash them to you, because I am very short of time. And to make a long story short, this is an important transparency. You start with a reactor, which is a homogeneous mixture. There's no molecule there which has the properties, for example, of being amphiphilic. It is a chemical solution. The chemistry actually makes the system, when you illuminate it with light, the photochemistry starts. And here is what happens when you get this. This appeared in 2017. And let me see if I'm able to show you. This is actually a microscope picture. You're seeing the scale is 15 microns. And out of a homogeneous mixture, these guys appear. These are vesicles. Let's look at this guy. He cavitated, collapsed, started again. Cavitated, collapsed, continued, and he does it all under the control of his chemistry. No biology, no no biochemistry, no complicated stuff here. And we can do 40, 50, 60 cycles, and degradation sets in, there is replication, you have population, the population growth, you saw that the system was self-replicating there, then there's chemotaxis, there are a bunch of things going on that we understand. We also are able to do the same process with something like a chemical computer put inside. We can actually make, there is a catalyst there, and by using different catalysts, we can actually put them to compete with each other by introducing the form of click chemistry, which we introduced last year. And you can actually see how the system adapts, and to make a story, a long story short, you can actually, this is just essentially a repeat and a recap, but the main conclusion is that perhaps, like Stephen Jay Gould said in this, editorial published in 1996, when the Martian meteorite was discovered, he says here, and I learned about this just a 3 months ago, the origin of life may be a virtually automatic consequence of carbon chemistry and the physics of self-organizing systems, given favorable environments and requisite inorganic constituents. So, in the interest of time, here is my sponsors, always thank you to them, and the NSF funds a major center that we have in Harvard for actually looking at instrumentation, looking at the results of our experiments. And if you have, I am at 22 minutes, I think, from the beginning. So if you have questions, or besides the ones that I would like to please ask you to formulate now, you can always get in touch with me. And if you want to look at this, our group and the many very interesting young colleagues who are as responsible for this as myself, just look at it. Visit this top-down synthetic biology is how we call this website. Thank you very much for your attention, and I hope you learned something.
All right. Here we are. Thank you so much for your talk. I was wondering, John von Neumann wrote a theory of self-reproducing automata.
Hang on a second. I'm having trouble understanding.
Yeah. So John von Neumann wrote the theory of self-reproducing automata, and I'm sure you know what it is.
Yeah.
There is a tape. There's a tape with instruction. There is a universal constructor, and so on. Does your approach capture that, or is it completely orthogonal?
It's not orthogonal at all.
Okay.
The equations that are wrote down for you are stochastic cellular automata.
Okay.
Okay?
Mm-hmm.
And the tape is not in this particular construction.
Exactly.
But there is the equivalent of the tape. The tape is a ways of storing information, and the tape in those automata, which are related to Turing machines, is a construct where you can write and read, and you can also erase. Well, here the information is in the structure of the molecules. When I showed the reactor that we used, which is evolved quite a bit, each new generation of postdocs introduces their own. When you look at that, you see that there are a number of molecules there which are a few. Those molecules were there here. Okay? Water, acrylonitrile, for example, monomer, polyethylene glycol, something that's called a Rath agent, which contains a few carbons, and sulfur, which is important for polymerization. Ruthenium, ruthenium, which acts as a catalyst for the light, to look at the light and then transfer energy to the sulfur. So when you do that, the choice of materials is the information. Okay? So the information, this chemical information, is so-called configurational information. Mm-hmm. It's not genetic information, and that's a challenge that we're now addressing in the lab. Can you make this into polymeric information?
Exactly. At some point you will need a tape that contains all of this.
All of this is already put in, I mean, the information is there, and there is a tape here in some way.
Okay.
Okay?
Yes.
But a tape is necessary, polymeric information, I think, is an essential part of life,
Exactly.
as you and I know.
Yeah. Great. Thank you.
Anytime. Thank you for your question, San.
Hey, Juan, this is Lauren. I'm way back here. Firstly, that is just fantastic accomplishment, and it's a great talk, and I'd like to congratulate you on that. And you know, I find it funny that this kind of thing has not penetrated. I just have a comment. I don't have a question, but that this has not penetrated the origin of life community in the sense that what you've demonstrated is that evolution does not require template-directed synthesis. It doesn't require RNA, and it just seems like this is the beginning of something really new, really big. I think it's just fantastic.
Well, I think, yeah, it's very interesting. It's the product of the mind, okay, and the hands. But I believe what you said. The only thing is that humility is very important.
Stay human, yeah.
Before you get drunk. But I agree with you that that is true.
I think that
Thank you.
this has not penetrated our community yet, and it really needs to.
Thank you. I believe so too. Thank you.
Well, thank you very much then. I think we'll move on from there, unless there are any other questions.
Okay,
Thank you very much, Juan.